Hey guys, welcome to my channel. I'm LeetCode. If you guys are new here, I pretty much do LeetCode style questions and explain things in the simplest way possible. Today we have an amazing problem, so let's quickly go ahead and read the problem statement, guys. Right? So it says convert sorted lists to binary search tree. Right? So this is a very good problem. Right? So it says given the head of a singly linked list, right, where elements are sorted in an ascending order, convert it to a high balance binary search tree, right? So we'll be given a linked list, right? And our job is to convert it into a binary search tree, a balanced one that is, guys, right? So this is already sounds very similar to another problem that we did, guys. So let's proceed, right? So we see we'll be given this linked list, right? And yeah, so now the our job, right? Like we said already, right, is to have a balanced BST, right? So this is, you can see this is pretty well balanced. So it looks like they did a pretty decent job at making it balanced. So if it's empty, all right. So we already know sub. So this is just the same problem as the convert it into a sorted, where you have a sorted array, right? Um, but this time we have a sorted linked list, right? So just different data structure, right? But guys, the logic stays the same as the other problem, guys, right? And I highly suggest you go check out the other problem. I think this gonna make a lot more sense to you once I go through it, right? So since they want to balance, guys, right? That means that we need to make sure that everything's evenly distributed, right? You know what I'm saying? So to do that, right, we're gonna have so we're gonna first we're gonna choose the middle element, right? Just like as you can see visually, you can see how they made it balance, right? I'm saying so they just picked the middle element, right? And they just distributed everything accordingly, guys, right? So you see that so for this one, right? So zero, and then everything on its left, right? I'm saying that came before zero, right? It's gonna be on the left side of zero because, guys, right? Those are all the numbers that are smaller. So and we also need to organize it because they want a binary search tree, right? So we know the properties of a binary search tree, right? You know what I'm saying? We know that all the elements to the left are smaller and all the elements to the right are bigger than that particular node's value, right? That you're referencing, you know what I'm saying? So because of that, we're gonna be able to solve this guy, right? So we're gonna do the same logic as the other one, right? We'll be choosing the middle element, right? You know what I'm saying, as the root node, right? And we're gonna keep doing the same logic for all of different subtrees, right? So we're gonna pick the middle element as a root node, right? And then now divide it in half, guys, right? We're going to, so now we're gonna recursively pass in some bounds, right? To kind of restrict the space, right? The search space that, you know what I'm saying, the space that needs to be uh, converted, you know what I'm saying? So pretty much a divide and conquer algorithm that you could kind of think of it like that, guys, right? So, and then we do the same thing on the right side. We divide it, right? So all the number that comes after zero, right? We pass it to a right subtree, right? So that they themselves could construct uh, the BST, right? In a balanced way, right? By using the same logic, right? The middle element should be the root node, right? And then everything to your left, there's elements, right, that still needs to be processed, right? You're passing to your left subtree, and then if there's elements to your right, then you pass it to your right subtree so that they could be so that they could construct the PST as well, right? So that's kind of the logic behind it. It's the same logic, right? Finding middle element, right? And everything to your left, you pass it to your left subtree. Everything to your right, you pass it to your right, right? Just the same logic, just different data structure, guys. That's kind of the main takeaway, right? So, since the different data structure, right, the logic to find the middle element, right, it's gonna be different. And in an array, right, we got random access, so we could easily calculate that and get a one, the middle element, right? But not for this one, right? We're gonna be um, I'm gonna have to, you know what I'm saying, do we have already done problems using finding the middle element, which is finding the middle element by using the two pointer technique, guys, when it comes to linked list, guys. I got a playlist on that. So you guys should check out the two pointer technique, guys. So this is where it comes into play. And now the problem, it shows you that I'm saying this is a skill that you want to make sure you master because there's a lot of problems that uses that technique, guys, that you need to know that, right? I'm saying very useful technique, right? So let's quickly go ahead with the implementation, guys, right? All right. So what we're gonna do, we're gonna see this pretty much the same code, guys. Helper. We're gonna pass in the head, guys, right? And then I told you guys we're gonna have some bounds, right? The bounds are gonna be so it's initially. So this is the same code as the other one, right? Where we had the head, right? So the head is the first element in the linked list, right? And null is the pretty much that's how you know you're done with the list, right? In a linked list, guys, right? That's how it operates, right? I'm saying. So we're gonna have our private function right there, helper function. So we're gonna take in, guys, the list head, right? We're also gonna be taking in, guys, right? No, so let's call it the last node, or we could call it tell. Doesn't matter. This is the tell, right? The last node, in what I'm saying, tell of the list, right? Which is null, right? So initially it's null, right? So I know you're at the end of the list, guys, right? Um, so we know when we're done, we're the head of node equals to the tail, guys, right? If that's the case, we return null. We don't like those cases, guys, right? So after we do that, guys, what we're gonna need to do is start our logic to find the middle element, right? Because we need that to to create node, right? The tree node object. I'm saying we need to create that, right? Add a value to where we need to find the middle element, right? And then to be able to divide, you know what I'm saying, divide it so that, you know what I'm saying. So once we find zero, right, you know what I'm saying, or I'm saying we could pass it into, so now when we call on our left subtree, right? So the bounds for the tail, right? It's gonna be the last one I'm saying. It's gonna be the slow, right? What I'm saying. So pretty much once you get to here, right, you're out of bounds. What I'm saying. Once you're so now only so on the left subtree, right? Only those two nodes should be taken into account, right? This node should not be taken into account because it's out of bounds, right? And then now we on the right subtree, we're gonna be calling slow that next to um process our right side, guys. Like, you'll see how it makes sense, guys. Right. So this node, so we got our slow pointer, right? Which is gonna be head, right? So we know the slow pointer, guys, is gonna help us in moving um twice as fast, guys, right? One step at a time, and the fast pointer is gonna be moving twice as fast, guys, right? So we know well fast that next, no fast is not null, and also fast that next is also not null, right? That's not the case, guys. We're going to be moving one step forward. Slow that. So go slow that next. And then fast. It's to go twice as fast. You fast that next. That next, guys, right? Moving it really, really fast. I'm saying. So once, you know what I'm saying, this condition gets hit, right? The slow will be at the middle, right? So we're gonna nicely be able to create our node that we want, right? So root is gonna equal to tree node root, right, is equal to tree node. And then we're gonna pass in, what we're gonna pass in, so slow is at the, I'm saying, so one thing that I almost forgot, right, it shouldn't be no, it should be tell, guys. That's how we know we get out of bounds, because we're gonna be dividing it in half, right? So I'm saying, so on the left, from the left subtree perspective, right, it shouldn't, once it reaches to zero, that's how we know it's done, right? I'm saying, because the bounds will be getting updated, you know what I'm saying. Yeah, that's why you're gonna need to do that, right? So that's why we have the tail variable to help us in restricting the bounds that, I'm saying, that we're considering, guys, right? And that, guys, well, then the last thing that's left. So let's call on our recursively calling. I'm saying, so for the left side perspective, right? So head stays the same, right? What I'm saying, and so now the end boundary is obviously slow. What I'm saying, and then we do the same thing for our right. So now helper. So we pass in our slow that next, right? So now that's the beginning boundary, right? I'm saying. So anything from like here and onwards, that's fair game, right? To be on my right side, right? So this is what I'm passing down, right? And then now we still keep the right boundary as it was, guys. You know, it's not called a right, it's called tell, right? I'm saying pretty much the same logic as the other problem, guys, the array problem where we have to do that, right? You know what I'm saying, this is a medium one, what I'm saying. But the other one was an easy one, right? But it's the exact same logic, right? The only difference that, we are introduced with this linked list, right? And we need to, I'm saying, we need to do some a particular technique to find the middle element, right? So yeah, it looks like everything's correct, guys, right? Pretty much to do a quick recap, right? So we have our helper function, right? So also pretty much this is a function that's gonna help us and us to recursively build the BST, right? Make sure, and we're doing that in a balanced way, right? We're finding the middle element every time and creating so I forgot to slow that down, right? We need to do that, right, to put the value. So so we cursively found the middle, right? I'm saying, then we divide it in half, guys, right? I'm saying, and we keep updating the bounds so that we'll make sure that we know, I'm saying, that calls that we're making, right, the subcalls, though, they're still within the bounds that they're supposed to have, right? I'm saying, once we had the array one, right, we had the left and right pointers that were restricting the bounds for each of the calls that we're making, guys, right? So yeah, we update the calls accordingly. So let's press run code. I think where it looks fine just now. Looks fine, perfect. Let's press submit. All right, awesome, guys. We're able to pass all the test cases, guys. So I want to thank you guys for taking the time to watch this video, guys. If you guys found value, make sure to give me a like. If you guys are new here, make sure to subscribe, guys, because I'll be doing a lot of other videos just like this one. So thank you guys for watching, and I'll see you guys in the next one.